So in flash evaporation, we'll be needing three equations. One would be the equilibrium relationship between the liquid phase and the gas phase. And this should be provided by the problem. Then we will have to set up our mass balance. And then together with the mass balance, we need in this case the energy balance equation. So if this is a very simple representation of our flash evaporator, you have the F as the feed, V as the vapor, and L as the liquid. And you have the Z, Y, and X as the mole fraction or the mass fraction, whatever is provided by the problem of each of these, shall I say, streams respectively. Then this is how we set up the overall material balance. I think this is self-explanatory. And the component balance is patterned after the overall material balance. All you have to do is make use of the compositions Z, Y, and X. And then aside from these two, the material balance, you have the equilibrium relationship, as I have mentioned. So that would be relating X and Y. And you have this energy balance equation for a process that is adiabatic. If the process does not have will not have Q equal to 0, then you will just simply have to add Q on the input side, that is on the left side of the equation here, for the added energy that you need to equate to the energy of the living streams. So this is a problem that is not often encountered in distillation, but it just might come out of the board exam. Hopefully, your review center or the agency in which you're going to have your review will have a specific example on what a flash distillation is. In our case, there are problems also in our book that has flash distillation, but it's not, I think, in the case of Jen Couplis and McCabe. But you can have some examples of this probably in Colson on the volume that has distillation. Okay, but nonetheless, you will be using these four equations because in your material balance or in your mass balance, you have actually two options: the overall material balance and the component balance. Now, we go to the second of the first group, and that's the differential or batch distillation. And this is what we actually do in the lab. So it is a batch and a single stage distillation that starts with the steel pot, initially full, heated at constant rate. So in this process, the vapor form on boiling the liquid is removed at once from the system. Now, since this vapor is richer in the more volatile component than the liquid, it follows that the liquid remaining in the pot or in the steel becomes steadily weaker in this component, meaning over time, there's less and less amount of the less volatile component remaining in the pot or steel, with the result that the composition of the product progressively becomes weaker or leaner in more volatile component, or that is impurity starts to be dominating. That is if you allow the evaporation, or rather the distillation to proceed beyond the boiling point of that component that you want to separate from the original mixture that was placed in the pot. Now, the special distinction of this type of distillation is that the vapor form over a short period is in equilibrium with the liquid, and the total vapor form is not in equilibrium with the residual liquid. The residual liquid is the liquid remaining in the steel. Then at the end of the process, the liquid remains and is concentrated in the less volatile component, those that have higher boiling points, and is removed as bottom product. So this is your simple, very simple illustration of a differential distillation. And most of the time, and this you can really read from the handbook, the process of tackling problems related to differential or batch distillation uses graphical integration. A graphical integration that was also discussed in your integral calculus then. So that's how it's done, or that's how we partly accomplish finding the required information for these types of problems. The third type is the steam distillation, the one that uses steam for higher boiling components. Now, this steam distillation is a process which consists in distilling water uh, together with other volatile or non-volatile components. So the steam from the boiling water carries the vapor. So the steam carries the vapor of the volatiles to a condenser. So this is used when your components in the mixture have high boiling points, where both are cooled and returned to the liquid or solid state, while the non-volatile residues remain in the boiling container. You will see this particular process being applied or employed on recoveries of oil, essential oils that is. And this is the video.
How steam distillation works. Most essential oils are produced by steam distillation. Steam distillation was invented around 1000 AD by Persian alchemist and healer Avicenna. It is in practice for thousands of years since then, and is still one of the best ways to take freshly harvested or dried plants and extract pure essential oil. Take a look at this distilling apparatus. The bottom reservoir is filled with distilled water. Above is an alembic chamber that holds the plant material, often called biomass. The biomass is full of tiny sacs that contain essential oil. When the water boils, steam passes up into the chamber. As the steam passes through the biomass, temperature causes the tiny sacs to burst open, releasing the essential oil. The essential oil rises up with the steam. Together, the oil and steam pass into a tube. This tube passes through a cold to mixing chamber. The cold temperature changes the steam back into liquid, which drips out of the tube. The liquid collects in a new reservoir, where the water and oil separate naturally. The water, which is called hydrosol, is left at the bottom, while the oil rises to the top. And lastly, the essential oil can now be collected and bottled.
Okay, that's your steam distillation. Now under type 2, and this is the focus of our most of our calculations, we have extractive distillation, we have isotropic distillation, and the case of rectification. That is the usual distilling process that is used in the industry. So you can refer to this figure in your handbook in this section. Now, aside from the rectification process wherein you have a liquid reflux returned into your column together with your feet flowing down as liquid, flowing countercurrent to the vapor that goes up, we have also under method 2, extractive distillation or azeotropic distillation. So in the case of extractive distillation, this is employed when the volatility difference between the components present in your mixture is so small that a very large number of stages would be needed, meaning the difference in the boiling point temperatures of the components are not that big. So in terms of separating them, that would be difficult and resulting to a column that will be very tall. Okay, so to address that problem, a mass separating agent is used to increase the volatility difference. That way, in terms of designing a column, your column will not be, will not be that tall. That way, we can separate these components that have only very small difference in their boiling points. Another one is azeotropic distillation. So it's an alternative to extractive distillation. So if this one could not be used, then we can have what we call as azeotropic distillation. From the term itself, azeotropic, this is used when your particular feed mixture reaches in the processing a temperature wherein they are already azeotropic, meaning you cannot separate them already. Then again, you can use the mass separating agent to increase the difference in the volatilities of the components present because they cannot be separated anymore. And that is in the case of azeotropic distillation. So we only have two groups, the group that does not have reflux liquid and this one, the one that has reflux liquid. Now, in your book, I think I have snipped this exactly from McCabe or John Kuplis. This is how your distilling column with reflux is illustrated. So this is your still. Your feed is being introduced somewhere here in the column, but you will learn later on the specific section where the feed stage is located. And then you have your reboiler here. The reboiler gets a part of the liquid that is collected at the bottom of the still and turns that liquid into vapor. So it turns that liquid into vapor by using steam. That way there will be vapor that will go up the column. Now, initially, we don't have that, as I have mentioned. Now, the rest of the liquid that was not turned into vapor is withdrawn as bottoms liquid. Now, for the vapor that goes up, you have this vapor introduced into our condenser. The purpose is turning it into a liquid. The liquid is part of that returned into the column in the form of reflux. The rest of the major portion is withdrawn as your final product. So this is how a very simple distilling column works. That is the column which has a reflux liquid. You have a video of this. Sorry, class.
Once crude oil comes out of earth, it is in raw state and cannot be used directly in any way. It must be refined to make it into usable products. Depending on the type of crude oil, it is treated by different refining processes to turn it into many useful end products. Mainly these products are fuels, lubricating oils, waxes, chemicals, plastics, and many other products used every day in modern society. The refining process takes place in three steps to change the crude oil into finished products. In this process, the first step is to separate the crude oil into its naturally occurring components. This is known as separation and is accomplished by applying heat through a process called distillation. To simplify the process, we consider one tower where distillation process is taking place. The crude oil is supplied to a furnace before the distillation tower, where crude oil is heated and vaporized and it becomes the crude oil mixture. The vapor and liquid mixture is then fed into the bottom section of the tower. The feed section is the hottest point in the distillation tower and can reach as high as 400 degrees C. Components that are still liquid at this elevated temperature become the tower's bottom product. The components that are in vapor form rise up the tower through a series of distillation stages. The temperature decreases as the vapors rise through the tower and the components condense. Yield from a distillation tower refers to the relative percentage of each of the separated components, known as product streams. Products from the distillation tower range from gases at the top to very heavy, viscous liquids at the bottom. In all cases, these product streams are still considered unfinished and require further processing to become useful products. Like products, glycans are further separated into propane, normal butane, and isobutene. This stream is often referred to as liquefied petroleum gas, LPG, and is sold as a cooking and heating fuel, naphtha, to be blended into motor gasoline, but is more likely sent to a catalytic reforming unit or octane improvement. Kerosene is generally treated and used as jet fuel. Heavier distillate streams are also treated and blended into finished diesel fuel or home heating oil or are further processed in conversion units such as fluidized catalytic cracking and hydrocracking. The routing of these streams will vary as product demand changes to either maximize diesel production or gasoline production. The lowest end of flows, asphalt, power generation and marine
The reason that I have shown this particular video is there was a mention, if you are keen to listening, that after the preheating in the furnace of your crude oil, the feed that is introduced into the column is in the mixture of vapor and liquid. The normal distilling column only receives liquid feed. Most of the time, it's either subcooled liquid or saturated liquid. That if it's a saturated liquid, that makes the problem a lot simpler for you, for us. But if the feed that is introduced in your distilling column is in the form of a mixture of gas and liquid, that is what is actually happening in the industry, then you will have a set of a different equation, or you will have a different equation to use in determining what we call as the Q that will be discussed in the second part of the slide under distillation. And if you notice, there are fractions, or there are what we call side streams that are withdrawn in the fractionating column. Each of the side streams would have their own some form of reflux liquid returned to it. That way, that particular what you call side stream in that particular section will have an increased product purity in terms of the stream that is being withdrawn in that particular section. Because in the video, you could see that there are several sections in the column where a particular product is withdrawn and further reprocessed into raw materials or either final products already in form. So that's it. So your feed is, if you're again keen in listening, is being introduced at the bottom of the column. Actually, to be specific, it's not really at the bottom of the column, but it's in the lower section of the column, which is the stripping section. So your feed plate, where your actual feed is introduced in your column, is located in the stripping section. The stripping section is the lower part of your column. The enriching section or the rectifying section is in the upper part of your column. Okay, now in most of our calculations, let me just go back. Okay, it's okay. In most of our calculations, we will not be using Ponchon-Savaret method because this one will be using the energy balance together with the material balance, which comprises the overall material balance and the component balance. When I was a student, we were taught how to do Ponchon-Savaret method. The thing with Ponchon-Savaret is your process is comparable to, if you can recall, in your heat and mass transfer, in evaporation, wherein you do energy balance. And then there's a portion that you need to go back and check whether the value that you have acquired is already acceptable. If not, you are to go back to a particular step in the procedure. It's the same thing with Ponchon-Savaret, and it's a trial and error thing until and when the conditions that goes with, I think, two steps in the process of computing for the required information are met. If not, you were going to do, if compared to a computer programming, a looping procedure until your value is acceptable in terms of what is stated in a particular step. So now, in your case, it's not anymore dictated that we discuss Ponchon-Savaret, but it is more accurate. Actually, the problem is accurately solved using this particular method. But McCabe-Thiele is close to the Ponchon-Savaret method, or arrives at the values that are comparable to that if you're going to use Ponchon-Savaret. Now, one particular thing that actually there are two things. So you're using energy balance in Ponchon-Savaret, and another thing, you are not assuming that there is what we call constant molal overflow. Now, this one is the opposite with McCabe-Thiele, which we will be focusing on. McCabe-Thiele assumes that there is constant molal overflow. What does this mean? Constant molal overflow assumes that the amount of streams, for example, let's say a liquid stream that enters and leave a particular stage or tray, is the same or constant. Now, if you're going to think of it in the, shall I say, in the common sense thing, how can it be constant wherein a particular component is being transferred already or turned into vapor? So how can it be that the mass of the liquid that is entering a particular stage and leaving a particular stage is the same? in McCabe-Thiele, it is assumed to be constant. So meaning if there's a decrease, and actually there is really a decrease in the amount of the values of the stream that enters and leaves a particular stage, so it could be either the vapor or the liquid, but that particular decrease is negligible. So that is why in McCabe-Thiele, it's assumed that this particular change is negligible. But in the case of Ponchon-Savaret, we don't assume that it is negligible, meaning the value of the streams that enters and leave a particular column, I'm referring to the liquid and the vapor, they are equal in McCabe-Thiele. In Ponchon-Savaret, they are not equal. So there are two things that differentiate the two methods. So this is where our focus is, the McCabe-Thiele method. Even our graphical approach is based on McCabe-Thiele. Now, it's based upon the representation of the material balance equations as operating lines on the X and Y diagram. Mentioning here the operating lines, you will learn what are these operating lines in our next session that would be on Monday. Okay, the operating lines are made straight by the assumption of constant molal overflow, which eliminates the need for an energy balance. So since we have assumed that it is constant molal overflow, we have what we call operating lines, meaning they are straight. If we don't assume that it's constant molal overflow, then these operating lines won't be lines, but rather they will be curves. So the liquid phase flow rate is assumed to be constant from tray to tray in each section of the column between the addition of the feed and the withdrawal of the product, which makes the vapor rate to be constant as well. This is the constant molal overflow that I have mentioned to you a while ago. This is the constant molal overflow that I have explained a few seconds ago. So you can read more on that on section 13-18 of your handbook. Now, if we would do away with the representation of the downspouts here, the weirs where the liquid go down, this is the simple illustration of your column. You have the feed here, you have this condenser, the distillate, you have the reflux, and you have the bottoms. W is the representation of, and this is the boiled up vapor, a part of the liquid that was turned into vapor. This is your stripping section, and this is your enriching section. If you're going to do material balance, your feed should be equal to the distillate plus the bottom's liquid. The overall component balance on A, most of the time A is the less volatile component, or rather the more volatile component. We would just simply multiply the streams here that we have by the corresponding mole fractions. Okay, that's it. This is our enriching section, and we will have what we call an enriching section operating line here. It will be drawn on the XY diagram that I have shown to you a while ago. So this is one of the three operating lines that will be placed on this particular diagram if we are to learn how to do graphical in distillation. The enriching section will have this material balance, total material balance, based only on this cutout of the enriching section. Okay, you can refer to this section in your handbook, and you can read also from the soft copies that you have of John Kuplis and McCabe. This is the component balance based or pattern from the total material balance of the enriching section only. And from the component material balance, you'll be able to get the operating line for the enriching section. The operating line of the enriching section tells you how. We will have a specific example on that next meeting. Tells you how you're going to plot this line here on your XY diagram. But that line, speaking of an equation of the line, will have a slope, this one, the slope, and it will have a y-intercept. This is your x and this is your y. Again, I would like to stress and emphasize that this operating line came from the component balance in the enriching section. Now, it may not look the same here because this is your original component balance. Okay, but we have replaced this particular slope here, ln over v sub n plus 1, by the by this expression r over r plus 1, because normally we are not given this in the problem, but the problem provides us with what we call as the external reflux ratio, and it's a constant. So with the external reflux ratio provided by the problem, you will know the slope of your line. The slope of your line will be that external reflux ratio over the same thing plus 1. Okay? The y-intercept of the line will be the distillate, will be the mole fraction of A in the distillate, still using the external reflux ratio. Now, you may ask, is this given, the distillate mole fraction? Yes, most of the time, the distillate mole fraction and the external reflux ratio is given in the, or are given in the problem. So you have now an equation of a line. And I know by now you have memorized how you write or how you draw a line based on its slope and its y-intercept. So we will have it reviewed next meeting, and we will apply what I have discussed today on Monday. As for the stripping section, you also have a cut out of the lower part of your column. So that's your feed there. And when you do material balance and component balance, or overall material balance in this section only, and component balance, you will be arriving at an equation of a line that will be this line. We call this the stripping section operating line. So you already have the two lines. The stripping section operating line. In terms of drawing or depicting on the XY diagram of the operating lines, this line is drawn last. Because after you have started with the drawing of the enriching section operating line, the next one is the Q line. This one follows where the Q line and the enriching section operating line intersects. So, but nonetheless, this is the stripping section operating line. This is your material balance for the stripping section. This is your corresponding component balance equation. And by that, you will have this operating line. This line is the line that was shown to you a while ago, drawn at the bottom part of the XY diagram. Okay, I have 10 minutes, so I need to finish this one. Okay, now, I have mentioned that the stripping section operating line is the last of the three operating lines that are drawn in the XY diagram, because the second line after the enriching section operating line that is drawn is the Q line. The Q line. And this Q is defined as the heat to vaporize 1 mole of feed at entering conditions per molar latent heat of vaporization of the feed. This is how it's defined in one book. Another book defines it as the number of moles of saturated liquid produced on the feed plate by each mole of the feed added to the tower. So this Q will have a specific value based on the formulas that are provided, also based on the state of your feed. Is your feed saturated liquid? Is your feed subcooled liquid, saturated vapor, superheated vapor? Those things will have different values for the Q, or have different formulas to use in determining the Q. So if it's saturated vapor, you have this Q. If it's saturated, you have this. If it's cooled liquid, if it's superheated vapor, this one, meaning your Q is negative. If your feed is the one that was discussed in the video, partly liquid and partly vapor, your Q will have a value which is between 0 and 1. Okay, that's your Q value. Now, this is another equation that you can use in determining the Q based on the first definition here, something to do with the heat to vaporize 1 mole of feed at entering condition divided by the molar latent heat of vaporization of the same feed. So using that particular definition, this is how your Q would be. If your feed is cold, liquid, or superheated vapor, I'm referring you to equations 21.27 and 21.28 of the 7th edition of McCabe. That's found on page 679. So I leave that to you to check, because anyway, this book has soft copy online. In here, if you're going to use the formula based on heats, so these are how HV, HF, and HL are to be viewed, or this is how they are defined. So enthalpy of the feed at the dew point is HV, enthalpy of the feed at the boiling point is HL, and enthalpy of the feed at its entrance condition is HF. Okay, we will have examples of that on Monday on how we're going to use this particular formula. So your Q line, when you draw it in your X and Y diagram, will have a slope which is Q over Q minus 1. This Q line is what we call class as the feed line also. So it's the second line that you draw after you're done with the enriching section operating line. Its y-intercept will be dependent on the mole fraction of the feed and the Q value, which we have correctly determined. If you're going to ask me what's the heart of correctly solving a distillation problem, I'm telling you it's the Q. Because if the Q is wrong, everything that you will be determining is wrong. Of course, it is a given that you know how to represent the diagram. The diagram already clearly illustrates that you have a clear understanding of what the problem talks about and what it is requiring. But when we go into already the solution part, the very heart of finding the required information in the problem, finding the Q is very important, because as I've said, the rest of the questions are really dependent on the Q. If Q is wrong, everything is really wrong. So that's how important it is. Now, how will the Q line look? So look at it, the Q now, this is your Q line depending on the condition or its condition. So if it's subcooled liquid, it's like this. If it's saturated, it's vertical. If it's saturated vapor, it's horizontal. If it's a mixture of liquid and vapor, it's somewhere here. Now, when you have drawn correctly your feed line or your Q line, same thing with your enriching section operating line, where the two intersects, for example, here, that's where you're going to connect the XW of your stripping section, or that is the mole fraction of the bottom's liquid in your stripping section. Then the three operating lines are now correctly plotted on your XY diagram. It's very important that you know or you place incorrectly the Q line, which, as I've said, is very also dependent on the Q. Just like any information that is required in the problem concerning distillation, is very dependent on the Q. The feed plate location, I think this is the last part, is the part wherein there is the change from the enriching section operating line to the stripping section operating line. What do you mean, Miss, with the change? Like if you're going to do a stepwise stair-like line in here, starting with the XD down to the XW, where there is a change in the location of these stairs or steps from one section, in this case enriching section, to the stripping section, that is where the feed is. But this feed plate or feed location is always placed, or shall I say, situated in the stripping section of the column. You can read that from McCabe. So it's only McCabe, I think, that mentions that your feed plate is on the stripping section or belongs to the stripping section of the column. Although graphically, you could see that the transition from the enriching section to the stripping section happens in the feed plate. A wrong way of determining the feed plate is this, wherein you made steps until you are done with the length of the line that you have drawn here. It should have ended here. It should have gone here. When you make the steps, it's not that you're going to make the steps depending on the line that you have drawn from for your enriching section, but rather you only pass this particular intersection right away. So pagkaagi mo daong adiri na intersection, transfer ka na dayon sa dalom. Hindi kay extend mo pa until matapos mo ning linya nga gindraw mo. If that is the case, your number of steps determined graphically will be very erroneous. The correct way of determining the feed plate location is this one. There is a transition right on the intersection of the three operating lines. Not that the transition will happen when you are done already making steps on your enriching section operating line. This is our McCabe-Thiele diagram. It's anchored upon McCabe-Thiele way of solving a distillation problem. So this is now your enriching section operating line. This is your stripping section operating line, and this is your Q line or your feed line. This is how you determine the number of steps. This will tell you how tall will be your column or how many stages you would need. That way you are able to separate or achieve a certain degree of recovery for your distillate, which is also given in the problem. What would be the mole fraction of your more volatile component in the distillate? Okay? When we want to determine the minimum number of stages, we don't need the operating lines because it's just like the operating lines are right on coinciding on the shall I say, the 45-degree line. Excuse me, class, huh? Hello?